Buenos dias. All right. My name is Patrick Dexter with a company called Cepstral, and today I'll be talking about text-to-speech software. We'll discuss how text-to-speech voice is made, the component parts of text-to-speech software, and how that fits into a unified communication software like Asterisk. To give you some background information on Cepstral, we're a commercial company spun out of Carnegie Mellon University in Pittsburgh, Pennsylvania. We have customers all around the world, from doing announcements in train stations in New Zealand and Australia to delivering thousands of concurrent calls in large call centers in Canada. Our main customer base is in North and South America, and we've been a proud partner with Elastix since 2011. Our marketing department wouldn't let me do this presentation without giving you our Twitter address. If you have any questions about this presentation or text-to-speech in general, during or after ElastixWorld, please tweet them to us. We'll get back to you as soon as possible. So what is text-to-speech? Text-to-speech is the ability to create spoken audio from words and phrases that were never recorded. There are far too many words to record them all, and new phrases like company names or people's names are being created every day. This is especially true that we see in telephone systems. You need to tell a caller the amount of money they have in an account, or the date that a package will arrive, or where it's going, what specific address. This type of information is constantly updated, so you need an efficient method to get it to callers. Before we dive into the details about text-to-speech, I want to show you one of the earliest speech synthesis devices. So what you're seeing here, this machine on the slide is a replica of the first speech synthesizer, originally developed by Wolfgang von Klempenin in the late 1700s. Interestingly, this replica that we see here was studied by Alexander Graham Bell. He created his own version of this and played with it and used many of the ideas when he invented the telephone. So this device directly went into the invention of the phone system. So speech synthesis and telephony systems have been used together since the very beginning. There are several different competing technologies that are used to create text-to-speech voices. If you're familiar with text-to-speech at all, you may have heard of these. Formant synthesis is a very interesting model. It creates mathematical models of the mouth and lungs and throat. And it's very small size, just a few megabytes, which is great, but they don't convey very normal speech sounds. To me, it sounds much like an opera singer. It's used a lot in synthesizers, Yamahas, Moog synthesizers. Formant synthesizers are only good at doing vowel sounds, and they're not very good at consonants. Diphone voices, this is what the Stephen Hawking voice is. So it's very robotic. It's easily understood, but it doesn't sound like a person. And then statistical parametric voices. These are called HMM voices for their use of hidden Markov models. And they create a model of speech based on a corpus of material and then use that model to generate new audio. Google recently published some very interesting research into this. This is sort of the cutting edge of text-to-speech, more research than actual production models. The primary technology being used in commercial text-to-speech synthesis, though, is unit selection. You're already familiar with this if your mobile phone talks back to you. It's what Siri uses on the iPhone. It's what Android phones use as Google Now. So today we'll look at the 5 requirements for text-to-speech voice. We've got the input text in phone systems, often from a database. Natural language processing to get an understanding of that text. Then you have analysis of the available recorded material that's actually in the software. Digital signal processing to put that all together. And then delivery of audio to the user. So unit selection voices provide the most human-like experience today. And that's because they're made with recordings of actual people. These recordings are identified and labeled to create a database of sounds. So we've all seen something like this in movies and TV shows. You cut up letters, rearrange them to form new words, and at the most base level, this is what unit selection synthesis is all about. In English, there are 26 letters. In Spanish, 29, 30. So all we have to do is record about 30 things, 30 letters, and we have a unit selection text-to-speech voice, right? No. Unfortunately, it's not that easy. You can't record just the alphabet because human speech is not made up of letters. We use letters to write down speech, but when spoken, speech is made up of sounds which we call phonemes. And how these phonemes are pronounced can vary quite a lot depending on what you're saying and, more importantly, where in the sentence you're saying it. So much so that there are actually specialized alphabets specifically for phonemes. So let's take a look at some of these. I tried to modify this presentation with Spanish when possible. We'll see how it works. So agua is a word that even with my limited Spanish skills, I can kind of pronounce. And here's the phonetic spelling of that word. All right, you can see it's a little bit different than the actual spelling. If you're curious, this alphabet is based on the Carnegie Mellon University phonetic set. There are several other phoneme dictionaries. IPA, SAMPA are popular, but we use a variation of the CMU alphabet for our technology. Okay, so kind of going through this, looking at the first phoneme, we are depicting the ah sound. We have a 1 on it, which denotes that the vowel is stressed. G is represented by G. And here we have one that's new, XU with an O. And this is where phonetic alphabets start to differ from a regular alphabet. If we just use the U to describe this sound, it wouldn't work. Aquí, it's a very similar word, has a U in it, but it's pronounced completely differently. Aquí versus agua. The wa is that difference. It's that XU phoneme. The O, again, marks it as unstressed. And the A now completes the word to give us that full W sound. So I think the really interesting thing about unit selection voices is that we actually need specific people to record a new voice. And once that's recorded, that technology, that software will live on beyond them. They could live on theoretically forever. So how do we grab all of those sounds, all of those phonemes? Well, we take that lucky voice actor, put them in a sound booth, and force them to record hours and hours and hours worth of carefully worded scripts. These scripts are designed to capture as many phoneme interactions as possible. We don't really care what they're recording or what they're saying. We just need them to get different sounds. So here's an actual sentence from our English script. This sentence is grammatically correct, which helps the voice actor to read it in a natural tone. And once it's been recorded, the audio file is segmented into each individual phoneme. The location in the sentence of the phonemes, in the syllables, words, common phrases, and then sentences is noted. And this allows us to better match the sounds together when the software runs. We'll see an example of this all working together in a minute. So I mentioned the phonemes are labeled. We're looking at a number of different features here. The phonemes are labeled with what we call acoustic parameters or context factors, like the fundamental frequency or pitch, the time duration, position in the syllable, and neighboring phonemes. Because of all these different possible interactions, when we're done, we'll have hundreds of thousands of examples of units of each phoneme in our database. So now that we have recorded a database, now that we have a database filled with units, we can select them to create new audio that was never recorded by the voice talent. So here's a group of words, most likely recorded days or even years apart from each other. We have to use the same voice talent to create each voice, or each text-to-speech voice. So based on our own testing, customer feedback, we'll record new material and build that into the voice in order to produce more natural synthesis. So let's go through this and create a new word. All right, starting off with agua again. You can see that we're grabbing several phonemes at the same time. The TTS engine is looking for units that will match up the best. So if we can find a phoneme that were near each other already, the audio is going to sound better. It's going to sound more natural. What we want is for the phonemes from different recordings to join together smoothly. If they don't, there's a jump in the two sounds. It goes like that. And it makes it sound robotic. It's that glitchiness that you hear in a text-to-speech system that sounds kind of robotic. So getting those smooth joins, it's of the paramount importance. That's one of the reasons why we need such a large database of audio. We need hundreds of thousands of separate units to get that smoothness. All right, so continuing along, now we'll add in some more phonemes. We're taking the duh sound here, building up the new word, taking in another phoneme. In an actual text-to-speech engine, this whole process actually takes milliseconds. This is how the software can be used in a telephone or unified communication system. It operates faster than real time. The engine will also be performing a number of other calculations as it does this. We'll take a look at that in a minute. To me, it's kind of still amazing that this technology even works at all. So finishing up, putting all the phonemes together, the Mexican city of Guadalajara. Now this is just a simple example of creating a new word. In real life, a TTS engine is looking at features like phrase boundaries. Does the phoneme occur at the beginning, middle, or end of a word? Going even farther, where in the original recording was the word? All of these attributes influence and have different weights and measures to determine what phoneme is picked. All right, so the w phoneme from agua in these two sentences are labeled quite differently. Typically at the end of the sentence, the pitch descends, it gets lower. Bebe el agua, and I know my Spanish is very, very bad, but el agua, the L bleeds, it joins with the A. El agua, it's different. So it would be very difficult to take that A phoneme and use it in Marta, for example. All right, so it's that M to A is very different from an L to A. The perfect unit required at synthesis time may not be available in the database. So a selection must be performed to choose from amongst many slightly mismatched units. So the more units we have, the greater chance that we'll find that perfect unit. So we talked kind of all about the research and science of speech synthesis, but there are actually real-world telephone applications that require this knowledge as well. Being familiar with phonemes and phonetic alphabets provides you and the end users, your customers of text-to-speech software, with the ability to customize the voice through what's called a user lexicon. User lexicons are lookup tables, replacing words in the text with user-defined pronunciations. These can be specialized acronyms that are specific to a company or people's names. This is often very useful when using an English voice, an English TTS voice, to pronounce Spanish or other language names. Lexicons fine-tune the audio to make sure it's understandable. I mentioned earlier that in milliseconds, the text-to-speech engine performs other calculations. One of the more important calculations is called text normalization. This actually happens first in the process. So let's take a look at that and what that means and why it's a challenge for all text-to-speech engines. So let's say you had, looking at this, what could this mean? It's a number of possibilities. Here in Buenos Aires, it could be a date, October 7th. In the United States, the date format is different. So to me, this would be July 10th. It's a bit absurd. I think we're one of the only countries to still use this format. I think it's because we hate the metric system. I don't know. I think we're just difficult. We could look at another way. This could be a math problem. These are the types of issues that text normalization or natural language processing has to solve. Unless the software knows exactly what the sentence means, it cannot properly pronounce the words to convey that information clearly. One of the keys to figuring out these things is identifying and analyzing them in the context of the sentence as a whole. So about a week before a dentist appointment, we'll receive a phone call reminding me to floss and brush my teeth so I don't get yelled at by the dentist with the sharp instruments in my mouth. If you have a service that provides outbound phone calls, this message is exactly the type of automation that text-to-speech is perfect for. All right, in a high call volume environment, there's no way you could record every name. And on the call, you really want to identify the specific person, in this case, Patrick Dexter. You don't want the wrong person to show up at the appointment. But even with saying the person's name, there's so much more here that a computer can easily make a mistake on. The text-to-speech software needs to identify this text, DR period, not as DER, but as the abbreviation for doctor, right? Dr. Steele is what a person reading this would think. So that is what that's what the voice has to say. So getting back to our date example, a text-to-speech engine should be able to correctly interpret this text as a date. It will look at the sentence and know that it's an English sentence. In English, steal, on, the on is a preposition that typically comes before a date. So that's a context clue. It's a very good clue. And since it is in English, we know the format for is month, date, year. This gives you an idea of the type of rules that are built into TTS engines. Some of the fun research right now that is being done in the field of computational linguistics is how to apply more sorts of artificial intelligence into natural language processing and into this process rather than strict rule-based decision trees. And we still have some more decisions to make here. At the end of our sentence, again, there's something ambiguous. The time of the appointment. If the TTS engine reads this as 10:30, that it doesn't make sense. It will cause confusion. So what it needs to do is say 10:30 a.m. All right. So this is kind of fun. Another issue are what's called heteronyms. Does anyone know what a heteronym is? Anyone? No? Okay. It's an evil part of the English language where a single word is spelled exactly the same but means two different things and is pronounced differently. I don't believe Spanish has heteronyms. If it does, if you can think of any, send me a tweet. All right, let's look at a couple examples of this. The word bass can be a fish, or it can be pronounced bass, and in music mean the deep low end, as in the bass clef versus treble clef. So it's spelled exactly the same, two different meanings, two different pronunciations. This is a fun word. This can either be a noun or a verb. In Spanish, this may make sense. I'm really hoping. I use Google Translate. But you have two different words for the verb and noun. In English, it's the same sentence. I object to that object. The different pronunciations of the exact same word, do you hear that? I object to that object. If you say it, I object to that object, to an English speaker, it doesn't make sense. The engine can figure out, the TTS engine can figure out how to pronounce these words by looking at the part of speech. All right, object that's identified as a verb, object as a noun. This functionality is called a part of speech tagger, and it's very helpful in text-to-speech engines. So currency interpretation is also important. And it's something we see all the time in telephone systems, right? Outbound call campaigns. Maybe this is a phone call to remind someone of a fine they'll have to pay or a utility bill. We'd read this as $10 or 10 pesos per day. This would be read as $10.5 million per day, not 10.5 million per day. So the engine has to look at the entire sentence. It's going backwards and forwards in advance in order to understand not only what the text is, but how all the words interoperate. Text normalization occurs first in order to determine what the text as a whole means. Periods and commas are interpreted to add pauses, signify numbers. Dates are converted into formats that are more friendly or more understandable when you hear them. Abbreviations and much more are all figured out so that human-computer interaction can occur. To put all these pieces together, we have our text-to-speech software here, right? We've got number one, the text is sent in. The text normalization occurs, trying to figure out all those dates and currencies, parts of speech, heteronym. User lexicons are now used, or check to see if there are any custom pronunciations that are built into the system. the best possible units from the database, from those hundreds of thousands of examples, based on all those acoustic parameters like pitch, duration, position relative to other phonemes. These are chosen. The units are all joined together to generate a waveform, and the audio is outputted to the user. In the world of telephones and unified communications, text-to-speech isn't just magic, though. It's an incredibly powerful tool giving you the ability to deliver information to your callers. Let's take a look at an example of how to do this. Since Elastix is built on top of Asterisk, we can use all the existing tools like ODBC database connections for grabbing variable information, and the open source module AppSwift in red for linking Cepstral into Asterisk. So we'll be looking at AppSwift, which is specific to our text-to-speech engine, but there's also a protocol called MRCP. If you want to use other text-to-speech engines, MRCP is also used to add in speech recognition. It's great for larger installs where you may have multiple Elastic servers or that all need to share a TTS resource. If you want to learn more about this, send me Twitter or talk to me afterwards if you have any questions. We'll look at an example with AppSwift, though. So Swift is the name of our TTS engine. So this adds the Swift command into the dial plan. It's a simple greeting and then uses asterisk functionality to listen for a DTMF dial tone. So we've had customers with hundreds of menu options, thousands of menu options. You can have a giant book filled with for their IVR. And this entire thing read is real time in TTS voices. So allowing them to make menu updates and changes on the fly. Want to add a new IVR menu option, simply reload extensions.conf and the menu changes. No recording of prompts, no uploading WAV files. It's very, very easy to maintain. So like I said before, with ODBC, you can also create very complex database-driven systems right in the dial plan. Or you could use AGI, if you're familiar with that. So here's a very simple example of querying a database for an account balance. And then using the Swift command right in the dial plan to read that back to the caller. Because you have the dollar symbol in there, Cepstral will perform that text normalization we discussed to read this off as a person would read it. So you can really expand on what's possible to automate inbound and outbound calls. Do you have a technical support line? Have the caller identify themselves with a ticket number and read back to them the last note that a customer service left, or a status update on a known system outage, right? If you receive huge calls that come in whenever there's something goes down, make an automatic recording or call outbound to everyone affected with an automated message. There's a fantastic video about this available from Elastix training that goes into detail on how to install and configure TTS and Elastix and how to get an AGI script set up that makes use of text-to-speech software. I'll tweet this out as well if you don't. I do recommend that you watch it. It's in Spanish, and you can pause and rewatch it over and over again. Now that you know how text-to-speech software works, it will make a little bit more sense when you're adding TTS to Elastic systems. All right, so in summary, to end, text-to-speech software is a powerful tool. You can read any information that you have to your systems. Not only is it useful for traditional IVR systems, but if you have a call center agent or customer service rep reading information to a caller, text-to-speech can automate that, allowing you to grow call volumes without adding agents. It also frees up agents to handle more difficult tasks that can't be automated. So gracias. Thank you very much. Really appreciate speaking here.
¿Preguntas? Aguarde que ya sé.
Yeah, one question regarding typing. For example, when you say doctor is DR point, if you have an address, Rodeo Drive, you have to type drive, right? Otherwise, it would be Rodeo Doctor, no?
No. So the engine will interpret the address information and learn, and it knows that this is an address, and it will say drive. At least it should. No?
Hola, buenos días. En tu experiencia, ¿cuán lejos estamos de la traducción simultánea? O sea, lo que están haciendo estas señoritas ahí atrás.
It's getting close. I can say that text-to-speech is not the problem for simultaneous translation. It's the difficult part is on the speech recognition side, and then the machine translation. Speech recognition systems work very well if it's trained properly for one person speaking. It's very difficult to get everyone's accents, everyone's different languages understood by a computer. If you're in a quiet room, it's very easy. If you're on the street, if you're in a store, there's people talking, lots of background noise, it's very difficult. But it is getting better. Moving speech recognition into the cloud has made it much faster and improved reliability and accuracy. So I think in the next probably 5 years we'll see it. Thank you.
Good morning. So you show us all the examples of the engine working in English, knowing the context to use the right pronunciation. How does it work in Spanish? Is it good enough or not yet?
No, it's very good. So all the principles of the technology are the same in English or Spanish or French or German, Italian. We support all of those languages. Like I said, we've worked with Elastix for 5 years now, and so the Spanish voices have been used throughout South America and Mexico. They are accented with Mexican sort of dialect, so they're not used very much in Europe. But at least we've had great success in South America with our Spanish voices.
Buenos días. La consulta, justo por lo que aparece en la pantalla, por ejemplo, se ha trabajado también en lo que son los tipos de pronunciaciones, por ejemplo, gracias frente a gracias, como aparece en la pantalla.
Okay. With the exclamation mark, the exclamation mark is difficult. It doesn't add in the emphasis there. A question mark will do that. But the exclamation mark it's difficult to kind of stretch that audio to make it louder. It doesn't sound natural.
Hola, buenos días. Quería preguntarte si el software te permite aprender o enseñarle o de alguna forma que el usuario tome el software y le vaya leyendo y a partir de ahí vaya aprendiendo y vaya tomando nuevas formas de hablar, digo, o interpretar distinto las palabras.
Do you mean to learn a new language?
No un nuevo idioma, sino en el caso, no sé, de la Argentina, donde cada provincia habla distinto, todos hablamos español, pero bueno, todos algo así, y que no sea un idioma neutro.
Okay. In order to do that, in order for different dialects, you would need to record a new voice with a speaker with that dialect. It's difficult to use the user lexicon to accomplish that. You could make some changes, like pollo or pocho, right? But it's very difficult to do that system-wide. So specific phrases you could change, but you can't change the dialect completely without recording a new voice with a new person. So our Spanish voice is, the voice talent is from Mexico City. If we wanted a Castellano voice, it would have to be from Buenos Aires. You can't take the Mexico City voice and magically turn it into Buenos Aires.
Está bien, gracias.
Hi, how are you?
Good, thanks.
As you were telling, we cannot agree on the same metric systems. How can we agree on the same languages will be even more difficult. What I was thinking, as you're telling that every city has his own pronunciation and its own grammar, and even differs from one side to the other, what I'm thinking is that we could even, right now we have the possibility to trace, get some AI on the phone companies to have the learning process to be faster than having a person to go into a room, and how the language will be degraded because of some people that doesn't have the pronunciation, all that, the machine could not learn properly the language. So that's what I'm thinking, to have a system that grows by itself. I've been using the automated systems for ticketing, and they're quite good, but they don't understand the problems that a person can have. Like the whole phone system is down, so you're telling the machine, can you bring that PRI up? And okay, we'll put an escalation on that, and that's it. It doesn't care about your problems and all that. So those are the questions I have.
Yeah, I think you bring up a number of points there, but I think trying to convey a message of empathy is difficult with a robotic voice, but it really gets into with what you say rather than how you say it on a phone system, I think.
Okay, and what about the learning process? Can we get some AI on the phone companies? Would that be ethical or not?
I don't know if it's ethical, but it's being done. The phone companies have a great amount, they have a huge amount of data. You have a corpus of material that is sitting there that will be used for learning by an artificial intelligence system. Every time you speak into your phone, for Google Now or Siri, that is being analyzed by Google, it's being analyzed by Apple. They're not just doing that for you for free. They're learning exactly how the language works and what the differences between those dialects are, and getting information about noisy spaces or information about rooms. It also knows where you are. All of that data is being analyzed right now. I don't know if the phone companies are doing it as well, but I do know that Apple and Google are doing that.
Okay, thank you.
Yep, thank you.